If you have friends who is joining or is in the waiting room, you just let me know, because sometimes I don't monitor that window. Okay, anyway, this one is talking about the definition of 1 volt. Okay, so the definition of voltage or potential difference is essentially the electrical energy converted to, I mean, it depends on what is between P and Q. Okay, so basically it's maybe if it's a resistor, then it will be electrical energy converted to non-electrical energy per unit charge. So just based on this, I can tell that, it has to be moving 1 coulomb of charge. Okay, so definitely not 1 electron. Okay, per unit charge means per coulomb. Okay, so now the question is just saying, are we moving the charge from P to Q or Q to P? So right now you imagine, okay, let me draw the circuit for you. We don't have anything between P and Q. Or rather, there's, for some reason, between P and Q, there is 1 volt. So maybe you can suggest what causes the P and Q to have to be 1 volt. Like I can't just connect the voltmeter to a wire and expect it to have a 1 volt reading, right? So what should I be connecting this circuit to? How should I complete the circuit? You might be thinking, can I put a resistor? Well, if you put a resistor between PQ, I mean, it can be like this, it can be like this. It's the same connection. It doesn't matter. But if you put a resistor here, then my question would be, the energy come from where? Or where would the energy for the resistor come from? Because the resistor itself is not a power supply. So the resistor itself can't convert its own energy. It's not going to happen. Which means in order for this voltmeter to have a reading, the only possible thing to connect this to is a battery. And since the voltmeter labels here as positive, and this one is negative, so we are probably going to connect, let's say, a battery or a cell, where the positive terminal is connected to the positive terminal of the battery, and the negative terminal is connected to the negative terminal of the battery, like this. If not, you won't get positive one. Okay. And now, let's say, for example, you want to move charge. So let's think about the current flow. In order for current to flow, assuming that this is an ideal voltmeter, I need to put something between PQ. Okay, there has to be something lah. Maybe I'll just stick a resistor here. All right, so your current will flow this way. This is direction of current flow, I. But where is the direction of charge flow? Because the reason why there is current flow is because there is electrons flowing in the opposite direction, right? So your electrons will be flowing this way. So your charge is from Q to P. So the answer is B. Okay. So you can treat the 1 coulomb of charge as a magnitude of charge rather than a polarity of charge. But the right movement of the direction of charge will be from Q to P. In other words, Q to P is the direction of movement of the charge. Okay, hope that helps. I'll just screenshot this and throw inside Discord. Okay. All right, so just sometimes they draw you half a circuit, you gotta find a way to complete it yourself based on the information given to you. Right, great. Glad you're okay now. So previously, we stop at our Newton's third law. This is chapter 3. We look at the 3 Newton's law. We focus on using the change in momentum over time equation, purposely on propulsion and also constant mass questions. So if you want to practice, the questions are selected for you, but feel free to go through the topicals, okay? And then we also look at collision, right? So I'm just going to add a note here that we also looked at the collision of so between two objects. And the important thing, just to complete the mind mapping, is that you can identify and apply the conservation of momentum. As usual, think about your 3 skills. Can you explain this? Okay, specifically link it to Newton's third law. Do you know how to calculate in various scenarios? Probably you do. This is the one that people are the most confident in. And also, can you reliably graph the changes in momentum? Okay. And then number 2, you should be able to identify elastic collision. So elastic collision, the definition here is basically the sum of KE is also conserved. But there is also a quick equation where you can find the speed of approach and the speed of separation. So in words, this is the relative speed of approach is equal to relative speed of separation. And we can add a layer of difficulty. I think I've talked to you about this before. We can have special cases. The first one is explosion, where the initial momentum is 0. The objects are not moving. And the second special case is 2-dimensional or even 3, actually it's not really 2-dimensional, 2-dimension collision, where we will want you to resolve the momentum, since momentum is a vector. Okay, so this one is a pretty good question to focus on, because definitely we'll expect 1 or 2 objective questions, and it may come out in combination with other chapters as well, right? Then chapter 4, you think about chapter 3 as y of motion, and specifically not just y of motion, the behavior of force. How does force behave, and how is it linked to the rate of change of momentum? This is the main idea of this section of chapter 3. And then we also started a bit on chapter 4, right? So in chapter 4, instead of talking about why of forces, we talk about what of forces. So normally when I label them, I call this dynamics 1 and dynamics part 2. Okay, so dynamics part 2 is more on application, basically what are the effect of forces. So if you look at your IG textbook, sometimes will say forces and motion, and then there will be like forces and pressure, and then there may be like forces and acceleration, forces and energy. You can see it somewhat like that. Okay, so the first effect of forces, before we can even talk about the force effect, is that we need to know the type of force, right? I've briefly run through this with you, but today we're going to continue here. So we're going to look at the type of forces, and you should be able to reliably identify when they exist if needed, and then draw them on the diagram. If you don't draw them on the diagram, you may not be able to do force analysis. Okay, so the type of forces that we have is your weight. This one is the easiest one. Everyone knows this is mg, pulling downward. Second one would be your normal contact force. So this is N. It exists when there are 2 surfaces touching each other. So we need 2 surfaces in touch, in contact. Normal contact force. And because when you see the word normal, think about 90 degree. 90 degree from the contact surface. Number 3, when 2 surfaces are touching, definitely you expect some form of friction or resistive forces. So normally we'll give it small f or a fancy looking f, but it can be any other symbol. Read the question. Okay, so this one, we need two surfaces in contact, but also the second thing is that it will oppose motion. So if the object is sliding to the left, we are also going to slide to the right. Okay, and then so basically, let me draw it for you. Let's say you have an object, it is on the surface or like a table, it's going in this direction, then friction will be in the opposite direction. Normal force is upward, 90 degrees to where it's touching the table. Weight will be vertically downwards. All right, pretty straightforward. And finally, we need to remember that there is tension, T. So we will only have tension if there's a string or a spring. And then the important thing to know is this is for pulling only. So if I draw a few diagrams, maybe if you have I think I've started drawing some pulley system, but let's say, I have a pulley system like that on two slightly different inclined planes, because why not? And I tie it to a string this way. Okay, so the tension T is used for pulling. We'll also do some questions involving this. Okay, but of course I didn't draw everything lah. There's also weight, mg, vertically downwards. Okay, there's also normal force, 90 degrees to the inclined plane. But why should we care about all of these forces, and what is the point of it? Well, the effect of these forces are many, okay? And I think the first few one that I want to identify that we're going to talk about is, number one, force can cause acceleration. Or in the language of your chapter 3, force can cause a change in momentum. Right, so let me box this up first. So this is like level 1. If you can't draw or identify the forces, you're going to have significant trouble moving forward, which I think with a bit of practice, it should be fairly straightforward. Okay, so the effects of forces are, number one, net force is equal to ma. Throw back to chapter 3. Force can cause change in motion. But change in motion here is basically acceleration or deceleration, but in physics, sometimes we just treat it as the same thing. So when using this equation, just a reminder, your F and A have to be parallel. If not parallel, what do? Resolve F. Okay? And then we ignore forces that are 90 degrees to acceleration. So for example, if I look at this green block and I pull it with some external force, maybe my hand pulling it with a certain tension or whatever. If I use net force, right, my net force here will be the external force minus friction. Because if it accelerates, it will accelerate in this direction. So I'm only taking the parallel ones. The 90-degree one, it doesn't affect the motion. Okay. All right, next. The second cause of force is net moment of forces, or torque. Normally from the question, it'll be pretty obvious what is the effect in focus on the question. But here, force can cause rotation. So there could be a net torque. Okay, so to find torque, we use the equation force times perpendicular distance. This thing is a vector. So all good physics students, especially if you already learned the maths, this is a vector or a cross product. Okay, but anyway, torque is a vector quantity. Normally, if it's turning clockwise, we give positive. Anti-clockwise, we give it a negative sign, normally. Just like this force is also a vector. Okay, so when using this equation, the important thing here is force must be perpendicular to the distance or the separation from a pivot. So this value of D here, maybe I'll move this one down. The value of D is the separation from a pivot. Separation from pivot. So maybe, I don't know, you have something like this and you hinge it here. This is the pivot P. So and you decide to pull it in this direction for whatever reason. So this one is the one that separates separation from the pivot. You measure the distance from the pivot. Okay. And as usual, if needed, the direction not nice, we resolve F. So resolving vector is basically a very important tool in physics. Whenever something is not in the direction that we want, we just split it into two so that we have one component that is parallel, the other component that is perpendicular. Okay. And here we're going to ignore force component that passes the line of action passes the pivot. Force of component whose line of action passes the pivot. Like for example, this line of action will pass through the pivot. So we ignore this one. Okay. So if you extend the line, it passes through the pivot, it's not that important. Okay. So since we know force can cause change in motion and force can cause rotation, if I want a system to be in equilibrium, this will be 4.2, then it is very important for my object to have two properties, or my system. The first one is resultant force is 0, so that the object is not accelerating, right? Resultant force is 0, and it has to be 0 in any direction. Up, down, left, right, front, back, if it's a 3D thing, okay? And number 2, your net torque have to be 0 about any point or any pivot. So then that force will not cause rotation, or the clockwise and the anti-clockwise will cancel off and you don't get any form of rotation. Right, so this is 4.2. So we've done quite a few questions regarding moment of forces. So today we'll do a few according equilibrium now. And then I will talk about the third and the fourth effect of forces tonight as well. All right, so we're going to look at some key questions from chapter 4. Okay, and we want to start by looking at a generic equilibrium question. So I have chosen the ones where the stick all looking a bit sangak, but there are more questions recorded in the YouTube channel. So refer to the official playlist and study from there, okay? I record complimentary questions. All right, so let's see. Let's say you want to evaluate equilibrium, okay? And you generally struggle with drawing forces on the inclined plane. This is one, okay? So go and practice this too. Ask if you have questions. Already did this. So we're going to continue by looking at focus B, which is how do you think about hanging cables? So as basically, whenever you see cable, just think about it as pulling only, unless it's a spring. Spring can compress lah, but most of the time, string or ropes are used to be pulled. So like for example, here you have a system. You can find a common point here, okay? And the cable and pulley is in equilibrium, and you're asked to find the value of R. So there are a few ways to do it. Of course, you can say, teacher, how to resolve? Everything is at some weird angle. Well, you can always define your own x and y axis. So let's say, for example, I realize that it will be useful if I have one axis in this direction. Let's say this is my x-axis, x. And then whatever I will have another one that is 90 degrees. This is my y-axis. Okay. So this means that my 1830 that is pointing in this direction can be resolved into two. One is here. Maybe I'll zoom in a bit. And the other one would be here. Notice that it is parallel to the y-axis here. And it's also parallel to R, which is also parallel to this one. So this one is right beside the angle. So side of the angle would be 1830 cos 35. All right. I repeat the same thing for the other cable. But then the funny thing is this other cable will also have the same tension, 1830. Same cable in the same system, same tension. Okay, so the first thing about tension is pulling only. Second thing, same cable, same tension. So right now, I just take all the forces that are parallel and equate them. So the green one will be 1830 cos 35. The blue one is also 1830 cos 35. They will both balance R. So you can find your R. Press calculator. Okay, so this would be approximately 3000 Newton. Of course, another way to solve this is to draw your diagram of forces. So maybe I'll pull this diagram, I'll pull this arrow here, I'll pull this arrow here. And I sort of have to make them, I mean, this is not drawn to scale, but I have to form a cyclic triangle. Okay, so it looks like R will be in this direction. So if you're pretty good at forming cyclic triangles, you can see when I extrapolate, it's like you can close the triangle, right? More or less. This one is just me sketching from the diagram. Okay. So once you can form the cyclic or the closed cycle, then you also sort of know that the force on the first cable is 1830 Newton. The second cable is 1830. Of course, you need to think about the angle. So the angle between R pointing up and the cable. So angle between R and the cable here is 35. Isosceles triangle, this is 35. So if you're pretty good at solving solution of triangle, you can use solution of triangles as well. But I generally prefer resolving because it's less steps. Okay. And here's another one. So calculation is always easy. The anticipation or the explanation or the change one is a little bit more challenging. So from here, you can see two pictures. Okay. And in both cases, the string is attached to the same points on the picture. So basically, I drill two holes in my diagram and I just hang the picture from here. I'll hang the picture from here. Okay. So after hanging the picture from here, you are asked which information about the magnitude of forces is correct. So I think the first thing I'll do is I'm going to resolve my forces, because what force is not drawn here is the weight of the cable. So let's say this one is W, or rather, maybe I'll just take this part, the nail. Okay. You can consider the picture, but I think it's easier for me to just think about the nail. This point is not moving. This point is in equilibrium. just like this point is also in equilibrium. At first thought, when I was thinking of using the weight of the picture, and I'm like, that's the W is here. So now I have to consider a fault force, and that makes me kind of meh. I feel meh about it. Would like to do less work. Okay. So right now you have these two. The point, this thing is hanging. So every single point on the picture is in equilibrium, including the nail. Okay. So right now you have these three forces pulling in this direction. If I resolve my tension T1, I will split this into two components like this. Okay. And then for T2, it will likewise be split into two components like this. Okay. So what I'm going to do is I'm going to think about the angle, right? So it is pretty obvious just by looking at this drawing that the main difference between the first diagram and the second diagram is the angle, right? In fact, if you want to, I'll resolve this so we can compare T2. So I'm going to resolve this one. Okay. So let's say this is theta 2. We do alternate angle, this is theta 2. And let's say this is theta 1. So this is theta 1. I think it's safe to say that theta 1 is less than theta 2. Can tell from the picture, right? Then now if I resolve, this downward component will be T2 sine theta 2. This downward component will be T1 sine theta 1. I don't care much about the horizontal component because left and right will cancel one. You see this one T1 cos theta 1. But also if we look here, this is a symmetrical drawing. So this is theta 1. Then this will be T1. So cos theta 1. So they are the same, so no big deal. Doesn't give me any information. But this is T1 sine theta 1 also. Which means I can take the two forces that are parallel to each other. Remember, these things are vectors and we want them to be parallel. So the upward force R1 is equal to the downward force summed together 2 T1 sine theta. Got 2. Just like, for example, this one, if you know they are equal, you can just multiply by 2. So it's the same thing here. Okay. So right now I'm going to repeat this one here. And my R2 is equal to 2 T2 sine theta 2. Now I need to compare these two equations and do a bit of maths, right? So first things first, it's pretty obvious that R1 and R2 will not be the same. Okay, how do I know? Well, let's see. Let me start with this one. Theta 1 is less than theta 2, which means sine theta 1 is less than sine theta 2. Okay, the bigger the angle, the bigger the sine of the angle. So right now, for equilibrium purpose, I have these two equations. R1 is 2T1 sine theta 1. And R2 is 2T2 sine theta 2. Okay. Then I look at my options. I am now supposed to compare both R1 and R2 and also T1 and T2. Okay. So right now, if I look at this question, right, the only thing I know is that this is the same picture. And because it's the same picture, it will have the same weight. Okay. So now I want to bring back the weight. Because if I look at this allows me to compare R and theta and T, but unfortunately, I have no information about R and T. So you could think about it this way. I'm going to crop the diagram again so I can draw on it. Give me a sec. But I want you to think about how would you include W into the equation. This is involving the nail. Now I'm also going to involve W. And yes, this is one of those questions where we used to, or Cambridge uses to filter the A-star candidates. You get about 3 to 5 such questions per year, per paper. It won't cost you your A, but it may cost you your A-star if you're right at the border, and it will cost certain people who are aiming for their top in the world awards, the top in the world awards. But it's not really that important. But hang on, let me find the question first so I can crop the diagram. In fact, if you look at the past year paper, they gave you an entire page to do this question, which I find hilarious. But anyway, get a sec to drag this down a bit. Okay, same picture. Huh? Okay, so we have already considered the nail, or rather this point as in equilibrium, but also the picture is in equilibrium. So if the picture is in equilibrium, there has to be a W here. There has to be a W here, right around the center of gravity, pulling it down. Okay, but what is holding the picture up? Sorry, the thing that's holding the picture up is this tension here, T1. Remember, rope is used for pulling, so it can pull on the nail, but the action-reaction pair would be pulling onto the picture. Okay, two different bodies. Nail pull picture, picture pull nail through the rope. Likewise, there's another T1 here. Okay. So if I only care about the picture, meaning if I only want to draw the forces acting on the picture, it is these two T1 balancing W. Okay, likewise here, there will be two T2 balancing W as well. We already resolved one, so we don't really have to resolve again. But what we're doing is we're going to take the vertical component. Vertical component here would be T1 sine theta 1. So 2T1 sine theta 1 is equal to W here. Likewise, 2T2 sine theta 2 will also be equal to W here. So in an interesting chain of events, because the weight of the object is the same, I can then just say 2T1 sine theta 1 is equal to 2T2 sine theta 2, meaning T1 sine theta 1 is equal to T2 sine theta 2. So far, so good. And this allows us to evaluate T1 and T2, because I know for a fact that theta 1, let me show you where is theta 1 again. Theta 1 is this tiny angle. Theta 2 is this big angle. So theta 1 is less than theta 2, meaning sine theta 2 is less than, sorry, sine theta 1 is less than sine theta 2. If this is the case, then if these two theta 1 is smaller than theta 2, how can we compare T? So you think about it as A and B, lah, right? So if this one is small, then this one have to be larger to compensate. Okay, meaning T1 has to be bigger than T2. So you can actually tell from the equation, because AB is equal to CD. You can also try numbers if you don't have a good instinct for equation. So 10 times 4 is equal to 8 times 5. Okay, so what happens when, let's say, B is small? Then this one will be larger. Small and large multiply will be the same. Okay, And then after that, what happens when this one is larger? Because sine theta 2 is bigger than sine theta 1. So you can treat this one as T1. I'm just using numbers as stand-in. Sine theta 2. 5 is bigger than 4. So this one will be a smaller. 8 is less than 10. In other words, T1 is bigger than T2 because the partner is small. T1 multiply sine theta 1. Theta 1 is small, so T1 have to be big. So the only one where T1 is bigger than T2 is B. Okay. And if you want to know why R is the same, well, we did this already, right? R1 is equal to 2T1 sine theta 1, which by the way happens to be W. This also happens to be W. So from here, R1 is equal to R2. Is it a bit of trigo? Not really. It's just, do you know how to sense the different changes when you have many variables? That's the challenge of this question. Okay. All right. So I'll leave you to these. You can try this first. Got problem, let me know. We continue discussion. It's a very similar question. The only difference now is we change the angle. Or rather, they start to talk about a lot of stuff now, okay? I think this is also recorded because it's fairly recent, but you can try out this question. Any question, you can let me know. It's essentially the same as this in 2014, modified to ask again in 2015, okay? So you can try the other equilibrium question. Sometimes it can be very easy. So I think I'll end with 2 easier questions just to comfort myself, comfort yourself. So here you have a heavy ball on the chain and a cable with a point of suspension. And the question is nice. They tell us to just think about the ball. So the forces that I have on the ball is the weight, the tension in the cable in this direction. Maybe I'll call this T1 for the cable, and the tension in the chain. So maybe I call this T2 question mark. So which one shows the forces acting on the ball? If the ball is in equilibrium, the net force is 0. So you should have a cyclic vector drawing. It has to be a cycle. So in this case, there are a few diagrams that are not cyclic. For example, this one is going down, this one is going down, but this one is also going this way. So no. A is sort of a cycle. Tension the cable going up, weight is going down, then going up this way. So you can see a nice cycle. This one is also a cycle. So this is still in contention. However, this one is not a cycle. So here plus here is equal to vertically down. So this is not a cycle. So the first thing you look for is cyclic. And then B and D is not cyclic. If it's not cyclic, means net force is not 0, not in equilibrium. So now we consider A and C. All right. So just by comparing this, the only difference I realize is the angle, not the orientation of the triangle. I don't care too much about that. I'm talking about the angle. The angle between the weight of the ball, which is accurately speaking vertically downward. So it's the angle of the forces between the weight and the tension, not less than 90 degree or exactly 90 degree. So I'll go back and stare at the picture. Where is weight? This tension in the chain is T2, right? This one down here is also tension in the chain T2. So is W and T2 90 degree or less than 90 degree? So I can extend the line of action of W. I have to make sure my W is pointing downwards, okay? And then my T2 is pointing upwards like that. So obviously this angle is less than 90. So this is your theta. The answer is A. All right, another way to draw this is to just move the direction of forces. So the way I'll do it is I'll just transfer all these arrows. So I know the tension of the chain will be in this direction. I don't know the length of the arrow because I don't know the values of these things. Meaning, I don't know what's the value of W. I don't know what's the value of T1 and T2. I just know their orientation. But objective question, right? I can transfer the arrows by just using my ruler. You know, the kind of half transparent ruler that you have. Just transfer the lines. Oops. Okay, so something like this. So which means the W should be longer, which is something like this. So you can pretty much tell that this angle is many things, but not 90. And you're thinking, where's the 90 degree? Well, my friend, the 90 degree is here. 90 degrees between T1 and T2. Okay, which basically is this diagram. So diagrams are straightforward. Calculation is also straightforward if you already have values. And since the angle is the same, because the tension is the same, I'm just going to use equilateral triangles. But I would take a point on the rope here on his feet as my equilibrium position. So at this point, he's 85 times G, 9.81. And there is a tension here pointing in this direction. There's a tension here pointing in this direction. So if you're feeling it, you can actually draw the vector triangle. You sort of have T in this direction, and then you will also have T in this direction. They are the same rope, so you have the same tension. Okay, you might be thinking, where is the 20 degree? Well, let's look at this one. This T is pointing upwards and to the left. This T is pointing upwards and to the left. The 20 degree is below the horizontal. Below the horizontal, 20 degree. Okay, so if you do alternate triangles, you can see this one is 20 degree. And because this thing is vertically down, you also know this is 90, this one is 71. Okay, and then you can repeat the process again for this T pointing upward, this will be 20. Okay, because this T is pointing upward. So it's pointing upward. And the angle is between where it's pointing and the horizontal, where it's pointing and the horizontal. Which means if you do alternate angle, this is 20, and this is also another 90 degree. So if you want to find T, you could easily just use half of the triangle. See this triangle here? So I just use this triangle. Because if I cut it in half, this is 90 degree, right? So I could use maybe sine 20, right? Sine 20 is equal to opposite 85G, but it's half of 85G. So 85G times half divided by T. So if you want to find T, it would be 85, 9.81 divided by 2 sine 20. So if you're used to using triangle, it can be a less cumbersome way for some people. I just want to show a variety of ways to solve the question. If not, you can always resolve. It is not a problem, whichever you are confident in executing, because this is an objective question. Okay, 1.2 kilonewton. Can it be in paper 2? Yes. In fact, I'll suggest a question. You go and try on your own time. This one in paper 2 is ON14 P23 question 3. Page 7 if you are using my topical handouts. Go try. All right. So we're going to level up our equilibrium and now look at stuff that involve a little bit more dimension rather than choosing a point. Like here, I choose a point in the middle. Here, I go and choose a point like the ball because the question is asking the ball. This one, I have to choose a point that is the picture itself. And sometimes I choose the nail, depending on what the question wants from me. So now we want a bit more dimension. So we can look at this question. It's fairly recent. And it's saying that a uniform rod is attached by a hinge at one end to a wall, and the other end of the rod is supported by the wire so that the rod is horizontal and in equilibrium. When you read a question like this, I can draw many forces, but I want to limit my effort to what matters. So find the thing that is in equilibrium and only draw forces for the rod. So the idea is please identify your system. Okay. So right now you have a rod and I only care about the rod. So the rod is uniform. Since the rod is uniform, the center of gravity is in the middle. So I'm guessing somewhere here-ish. So center of gravity is where all the weight appears to act on. So let's go put W here. Okay, what else do we have? We have tension in the wire. So the wire is used for pulling. So tension will be in this direction. I don't know the magnitude of this tension. I don't know whether it's big. I don't know whether it's small. I just know it's pointing in that direction. Okay. So which arrow shows the direction of force on the rod from the hinge? Okay. So here's a few comments. Number one, this tension, once I resolve into two, I realize that there is nothing to balance this force. This one is just chilling here. So which means the hinge will need a force in this direction to balance off the other one. Okay, so I'll write that down. I am just going to put this one as theta, okay? So this will be T cos theta, right beside the angle. So this one would also be T cos theta, so that it balances. Meaning I must have a force that is pointing from left to right. A is out, B is out. C is totally wrong direction. So the only option is D. But teacher, why is their D not just horizontal? Why is it also upward? Well, the great unknown here is I don't know where is the direction of friction on the hinge. Because the hinge is like a circle and I kind of don't really know where the rod is about to slide. Is the rod about to slide down or slide up? We don't know. But here is a shortcut way to do things. If I extrapolate the line of action of W and I extrapolate the line of action of T, they will both meet at this point, which means the third resultant force must also meet at this point so that the resultant torque is zero. So the net torque about this point becomes zero. So they have to intersect at one point, which means this force is actually the normal reaction force between the hinge and the rod. And the other force is friction. And it is the resultant force between N and F that gives us the force that is in this direction, pointing here. All right, so this is the shortcut. If you don't want to consider left, right, up, down, then you just resolve. And then you connect all the forces together. They should meet at one point. Okay. All right, let's look at another one. This one is nicer because you calculate and we all like calculation, right? So this one, you're asked to find what is the moment of this force about point X. So we are given the dimensions of the rod, the tension, the value of T in the wire, but I don't know the weight of the shelf. I mean, we can always label forces first and figure what we know and what we don't know. This shelf is attached to a wall at NX, kept horizontal to the wall as shown. Tension is 15, 30 degrees to the horizontal. So maybe somewhere in the middle, the midpoint, there will be weight, W of the rod. So you see, the thing is, I don't know a lot of things. I know 15, I know 30 degrees, and that's it. Do I know the normal force here? Well, I guess I can find this normal force. This normal force is, 15 sine 15 cos 30. So the force to the left must be the same as the force pointing to the right. I write the sigma to remind myself to sum down, but there's only two forces anyway. So pointing to the left is 15 cos 30 balanced with n. But you see, there is also a second problem. Second problem is I don't know the weight. So even after resolving 15 Newton and having a very nice 15 sine 30 here, I don't know W, and even more so, I would not know what is the friction here. Don't know friction, don't know W. So if I do upward force is equal to downward force, I put 15 sine 30 plus friction is equal to W. One equation, two unknown. This is not good. Okay. So then I have to be a bit smart. The question is asking the moment of force about point X. Since I use net force, I cannot. So I could use net torque. Net torque is 0. It means my clockwise torque, CW, will be equal to my anti-clockwise torque. And whenever we want to do this, we have to choose a pivot. I want to choose W as my pivot. It's a bit unconventional because most of the time you will choose point X as your pivot. But I'm going to choose this point as the pivot because, to be honest, I don't know what W is. If it's going to be in my equation some more, I can't solve it. So I'm going to choose this midpoint as my pivot. P. Can. You can choose any point on the shelf as your pivot. All right. Since I don't know F and I don't know N, to make my life easy, I'm just going to combine them. Okay. Combine them to be something like this lah. There, something in this direction. There. Okay, lo. Interesting scenario. So right now, who is clockwise? Let's say this is the force at X, Fx. So clockwise will be Fx. Okay. But you see, this torque Fx clockwise, by the way, turning in this direction, is actually the torque or the moment of force at X. This is what I want to find, right? So I'm going to keep it there because this is what I want to find. I'm just going to stick it here. I want to keep it here. Okay. Who is anti-clockwise? Nah, the 15 Newton. This 15 Newton. Or 15 sine 30. This 15 sine 30 is the one that is turning it anti-clockwise. 90 degrees when measured from W. So I'm going to choose midpoint or center of gravity as pivot. So the anti-clockwise will be 15 sine 30 multiplied by the perpendicular distance, which is the halfway point, 0.20. Why don't I care about 15 cos 30? Because the force is pushing in this direction. It doesn't cause torque. So this one, no torque or no moment. Okay, so from here, if I press my calculator, I'll get 7.5 times 0.2, which is, let me double check, 15 sine 30. I will get 1.5. So choosing the midpoint as the P. I resolve anything wrongly? One sec, let me dig up my own working. But the whole idea here is you actually don't need to know a lot of forces. And equilibrium question is always like a puzzle. One sec. Oh, I think I overthink it already. This is called baca soalan salah, or in Malay, read the question wrongly. Tension force in the wire is 15 Newton. By the way, this is correct. This is correct. This is the tension, the torque at X. Torque at X to balance or to cause or to balance the equilibrium. Balance the rod to allow it to stay in equilibrium. What they want, this is a classic case of overthinking, is this tension. What is the moment of this force about point X? So this one would just be 15 sine 30 about point X. So I need to choose this point, 0.40. That's what they want. So 7.5 times 0.4 is 3 Newton meter. Okay. But if they adjust the question a bit and they ask you what is the torque at X to balance the rod to allow it to stay in equilibrium, that is 1.5. I was thinking about equilibrium, so I was making the question a bit more difficult. So basically, I have set the question that I want to set rather than the question that Cambridge is setting. But in any case, if they give you this question and they ask you, hey, what is the torque needed at point X to balance the shelf? You can always choose the midpoint as the pivot, be a bit smart. We don't have to involve W into the equation. But in this question, they don't need you to find what is the torque at X. So it is not the moment of this force about point X or at point X, it is about. So when they say this force, they mean this tension force. So rephrasing so that it is the green color answer would be, what is the moment of force needed about at point X to allow the rod to remain in equilibrium. Okay. So if that is the case, then that will be 1.5. Sometimes I'm so used to doing difficult questions that I can't recognize an easy one. Okay. Anyway, I think the rest is fairly doable, or rather, they're all about the same. Like this one, we are also looking for cyclic drawings. And the only cyclic drawing you have is A or D. Because this one originate from the same point, so wrong. These two point towards the same point, so wrong. And you want the force acting on the end of the rod at point P, then you can take point P here, pull downwards. So I cannot have an upward force because I don't know what this is. So D. And in this case, you realize that this is probably tension here. This is probably weight down. But in a strange twist of event, there is no friction. The normal force passes through here. This is N. So the force at this hinge, right, is kind of mysterious one. It can be 90-degree, no friction. Let me draw all the options for you. If this is the wall, this is the rod, it can be in this direction if the friction is upwards and the normal reaction is here. In this case, friction is 0. Are there cases where it is pointing downwards? Yes. That will require you to readjust the cable a bit. But there are also cases where normal is here, but the friction is pointing downwards. All possible. Don't know. Need to read the question and figure it out. Okay. All right. So try out the rest, like this one and this one. And I think I will leave the rest to you to try regarding this equilibrium stuff. The main point here is to be able to use all of this information to help you find net torque. So I think I'll do one last paper 2 question before we go for a short break. I selected the one that look very Sangak one because they look difficult, but to be honest, they're not that difficult. Okay. So I want you to at least try to do this on your own on the handout or in page 23, because you see they give you a whole essay here. I can read and interpret for you, but that's not the point. The point is for you to be able to do it on your own. So go and read. But this is easy because the system or the object is in horizontal equilibrium. If your rod is horizontal, the question is easier already because you don't have to resolve forces, right? The spring, I don't know whether it's compressed or extended, but if I pretend to not read this, it says increase in length, right? So the spring is used for pulling. So if you pull, if you extend, you stretch out the spring will pull the system upwards. Okay. And then there is a pivot here. Pivot is already chosen for you. On the pan, you probably put some stuff. So you probably have to figure out where to draw the center of mass, where to draw the weight that we add in the pan. Go to the question. This one is actually quite easy. It's just that this thing, this 1, 2, 3, 4, 5 sentences scare people. Don't be scared. Go and read. Do it yourself. Okay. And another one is very recent from summer 22, where they combine equilibrium question with upthrust. It's very common. This is not the first time, it's the second time. Okay, so again, go try it. Let me know if you need discussion. Okay, I will do one where the rod is some weird thing, like for example, this one. Don't panic. The best thing is they draw forces for you already. You don't have to draw. Okay, or most of it is drawn for you. Okay, so for this one, you can see that there is a rigid plank used to make a ramp between 2 horizontal levels of the ground. Okay, and point A is at the lower end of the ground, and then it's sitting also at point B. This thing is held in equilibrium because there's a rope tying it down. This is like a ladder, you know, you're going to climb up some high building or the side of a cliff, you can tie a ladder this way. Okay, so the plank is held in equilibrium, so the thing is not sliding or rotating by a rope that connects point D to the plank to the ground. So D is here, ground is here. The rope is perpendicular to the plank, okay, already drawn, and has a tension T, also drawn. And the plank is at an angle of 38 degrees to the vertical. Okay, meaning here is 38 degrees, this side. The forces and the distance is already labeled. So normally they'll start you easy because this is paper 2. Paper 2 is easier. Show that the weight component that is perpendicular to the plank is 59. The weight is 96. So we are going to resolve one component perpendicular, okay, 90 degree to the plank, and one component parallel to the plank. So when we resolve it this way, right, what will happen is this one has no angle. So this is 96 sine 38. So because this is probably just 1 mark, I will just write 96 sine 38. Just press my calculator to check that it is 59. .1. So it's 59. It's okay to leave your answer at the same as they ask. Taking moments about NA, calculate the tension T. So I'm going to find A now. A is here. And I need to be able to identify all the perpendicular distance. The perpendicular distance of this 59 is from here to here. The perpendicular distance of this T is from here to here. And finally, thankfully, this 45 is also 90 degrees. So it's all the way from here to here. So we got to figure out who is clockwise and who is anti-clockwise. Right now, if I start from the 45, now it's going to cause this one to turn this way. So this is clockwise. Okay. The two anti-clockwise one would be the weight, the tension in the rope T, and also the weight component, the 96 sine 38. So clockwise is equal to anti-clockwise. And we can just nicely put 45 multiplied by the entire length. It looks like 1.1 plus 0.3 plus 1.5. Counterclockwise would be T multiplied by 1.8 plus 96 sine 38 is 59. If they give me 59, I'll use 59. This is 59. And this is 1.5. So you can easily find T. Although the diagram can look very scary, if the forces are labeled to you, then it is already half of the battle is gone. All that remains is you resolve all the forces. You find the torque for each force by choosing the correct perpendicular distance. Then multiply and give them the right sign or the right designation. Okay, let me press my calculator. 1.8. So my tension is 23.3 Newton. Let me double check. Okay, let that one. Right, 70 over 3 or 23.33. Okay, so this kind of question, when it comes to 3 marks, right? One of the marks is just you being able to write down any one of these correctly is 1 mark already. Anyone is 1 mark. The whole thing put together with the correct sign or clockwise equal to anti-clockwise is another mark. The final answer is 1 mark. So there are difficult objective questions that is worth 1 mark. There are easier paper 2 questions like this that's worth 4 marks. So please make sure you know how to do the easy ones. You don't know how to do the really difficult one, it's okay. We can practice it closer to the exam once you get the basics right. But don't give up, okay? Can one. Just resolve, take the one that's 90 degree, find the distance. Resolve, take the one that's 90 degree, find the distance. Okay, so go practice. I will leave the rest to you. But before I carry on, I want to suggest one for you to try that is a little bit different than the normal one, which is, and I think it's recorded. I don't know. Miss Ellie and I recorded 1,000 plus, almost 1,000 videos. I don't even know what we recorded and what we haven't recorded. May June 19 P22. But that's pandemic lah. Now we are so busy with work, half day all the time. Question 3. You know when you're tired and your brain default to its natural state? My natural state is always to assume that the question is harder than I think it is. Okay, anyway, you can do this one. Question 3. Page 14 if you're using my handout, because this one is a special case where it's a 2D object. See this one? This rod is one dimension, right? So you measure distance all along the rod. See this rod? This rod also one dimension. Huh? But what happens when you have a 2-dimension question? I'll go try. Okay, go do this one. And finally, just to explain to you what I mean by difficult, you see that questions like this, they never label forces. So do you know where the forces are acting? Question like this, no label force. Do you know where the forces are acting? What about this? What about this? So these are harder because there's no forces. Now let's do a speed roll through all the past year questions for paper 2. You see label forces for you? The forces is either all labeled or partially labeled. Like for example, they label this, they label this. You just need to label this, whatever X is. Okay, so whenever you do revision or you want to practice, you should start with paper 2 because paper 2 sets up the foundation. Okay, and then paper 1 is the one that we push in a bit to see if there's any gaps in your understanding or can you like extend your critical thinking skills. See, all this they draw for us already, very nice. See? Wow, nice, huh? They draw everything. Yeah, they draw everything, very nice. Okay, so we're going to take a brain break. For me, a voice break. And we're going to come back and just spend a quick time talking about upthrust, density, and pressure. This section should be fairly short. So in case you're copying, I'm going to save into the Google Drive in case you miss out any sections. If you have anything you feel like you want me to focus on, you can also let me know in the chat, either on Discord or on Zoom. But otherwise, go take a 10-minute break. I'll set a timer. Let me pause the recording first. Okay, thanks, robot lady. Okay, so we looked at the effect of forces. Okay, and then we care about the turning and the acceleration. Go try questions, right? And then the third effect of forces has something to do with pressure. Okay, but it is a bit incomplete to think of pressure without first thinking about density. Okay, so force can cause pressure. Okay, so just by this idea here, if the force is perpendicular to an area, there will be pressure. Hang on. Pressure P will be equal to F over A. As usual, the direction matters, although pressure is a scalar. So this is generally a slightly easier subtopic because we are dealing with a scalar quantity. Okay, the unit here is Pascal. So I guess if it's not Pascal, the unit can also be Newton meter square. Okay, just like this unit is Newton meter, and the previous one is just Newton. Okay, so this one, right, if whenever we do this, the force and the area have to be perpendicular. So this here, force, or basically weight causes pressure. But this weight here is the apparent weight. We'll talk a little bit about this later. But basically, force or weight is the one that causes pressure. Okay, so number one, F is perpendicular to A. So the classic example that you tend to see is maybe you have a cylinder like this. Then this is your surface area A. The weight of the cylinder is pressing down. This is 90 degrees. Okay, so force is 90 degrees to A, but we can also put this on an inclined plane. So if it's not 90 degrees, you know what to do lah. Resolve if needed. Okay, so I think I want to write that down. You should know by now. If it's not 90 degrees, resolve if needed. Okay, so from this force is equal to pressure. I mean, force is pressure times area, or pressure is force per unit area. We then sort of branch out to look at different scenarios, right? So the first one to think about is whenever I want to find the pressure, am I looking for the pressure in the solid? So normally if it's in the solid format or the general equation, we are using P is equal to F over A. This is the definition. But sometimes with some modification in liquid or fluid, so it can be liquid, it can be some kind of fluid. Pressure for gas is reserved for A2, but generally speaking, gas also can, provided you know the density. So that pressure will be equal to rho Hg. Okay. You need to know the derivation for this one. I think later there'll be some equations to derive, but hang on, let me draw a box around this first. So if you need to know the derivation, I'll put a D beside the stars. Okay. Is it important? Not really. I mean, it will be 2 to 3 marks in your paper 2. You decide how important it is. Okay. But you have to know, I mean, or rather, if you want to score that part, you should know how to derive this from here. Okay, this is equation number 1. Number 2, you should know how to use the instrument or the device. Instrument such as the manometer, your U-tube. Okay, they will put this one in mercury here. Then maybe another mercury arm here, this kind of U-tube. You should also know how to use a barometer, but barometer is not really that popular because I think barometer is an IG thing, but it is not in your syllabus, okay? I have seen questions like this before too. So this one, we place some mercury inside, but we are still using the equation P is equal to rho Hg. Okay. And finally, due to this pressure difference, so for example, if I have a tank that I fill it in with water, we know the deeper the tank, the higher the pressure. Okay, so in case you don't know how to use the equation, this rho is the density of fluid. Everything have to be SI, okay, if you want to have the unit Pascal. So density of the fluid that you are in. H is the depth measured from the surface. Okay, and of course, G is your good old 9.81. That's why it is the weight. Okay, let's say you have, I don't know, a cylinder here. Okay, and it is inside water. So the pressure on this top surface is due to H1, right? So the pressure here on the top surface will be H1, or rather will be rho H1G. And the pressure on the bottom surface is actually different because the bottom surface is lower than the top surface. So this is H2. And the pressure here will be rho H2G. So let's say this is P1 and the other one is P2. very important to know that it is the pressure difference, P2 minus P1, multiplied by the area. Area is obviously the area of the cylinder that is equal to upthrust force. Force is pressure times area ma. So upthrust is due to pressure difference. They like to trick student all the time. Because student remember the equation ma, right? Remember the equation for upthrust. This upthrust will be equal to rho Vg. So a lot of times you think about the weight of the water displaced. It just happens to be the weight of the water displaced, but the reason is due to pressure difference. Again, I'm going to put 2* here because you need to know the derivation. If you don't need, I'll tell you don't need, but these two you need to know. So you can go and watch past Miss Lee or past Miss Ellie derive for you. Okay, I'm going to do some questions. If you encounter a derivation, we'll do them. If not, let me know if you want me to talk about it. But we're going to focus on this part. And since we talk about upthrust, this is about floating, right? So under the branch of upthrust is the idea of density. No? You have studied this in your high school. Things that are less dense will float. Okay, we'll do some questions. All right. So we're going to now look at the, I guess, mainly the objective one first. So for density, right, most of the time, they will level up and talk to you about mixture density. There is a confirmed one question. I just don't know what kind of question they'll ask you. So we'll do one or two, but every year, every variant, you will find one around question 14, 15. Just pick a choose a few to do. It shouldn't be that hard. But in this case, we are mixing some oil together, and then you are asked to find the density of mixture. Okay, so right now I can find the total mass. The total mass of the mixture will be the sum of this one, right? Mass total. But do I know the volume? No. So I need to find the volume. Okay, so maybe I will just put a column here, find the volume. Density is mass over volume. So volume is equal to mass over density. 1200 divided by 1100. Okay. I think to save my brain some pain, I'm just going to leave it as fraction because this is not paper 2. Okay, so I'm going to repeat everything again, 1500 divided by 860, because I'm looking for the volume of this mixture. So this would be 75 over 43. Finally, 4,000 kilogram of this 910 density. (100 over 91). So if I total this, I can find the total volume just by adding all of this together. 12 over 11 plus 75 over 43. This will be 7.23 meter cube. So to find density now, I will take the total mass, 1,002, 1,005, 4,000, divide by the total volume, 4.23. I mean, sorry, 7.23. So I'll get 926.69, which is approximately 927. Okay, easy. It's not hard. It's just don't leave this to the first time you see questions like this, or practice so that you have a strategy. Okay, don't waste time. All right, so let's do another one, and I'll leave the last one to you. Okay, so actually I should do both because they're quite interesting. So all this is very recent one. I go and took everything from the summer 22 just to see the variety of question. So in the second variant, you see there's a granite rock on the surface of the earth with the density rho. the rock is transported to the surface of another planet. Okay. The acceleration of free fall on the other planet is twice than on the surface of Earth. Okay, so that means this G2 is equal to 2 times the G on Earth. What is the density of the rock on the other planet? What do you think? If you're thinking, well, if it's 2 times the gravitational acceleration, so 2 times the weight, so 2 times the density, well, then you have walked right into their trap because density is mass over volume. Did the mass change? No. I'm assuming that the rock is not being compressed or the volume relatively didn't change. So the density remains constant. Don't let them fool you. The only thing that is 2 times is the weight. Okay. So acceleration of free fall only affects forces or the weight, not mass. There. All right. So the other variant is a slightly different density question. It says here that the diesel engine expresses energy available from diesel fuel both as 41.8 megajoule per kg and 34.9 gigajoule per meter cube. What is the density of diesel fuel? Okay, so there are 2 ways to do it. One is I use the unit method, meaning I don't want to think too much about it, but my final answer should have kg over meter cube. Okay, so I look at this unit. The first one is megajoule per kg. I want the kg to be on top, right? So I'm going to flip the unit, kg over megajoule, because I want the kg on top. Okay, I'll deal with the mega later. Then you might be thinking, multiply this one by 34.9 gigajoule per meter cube. And the joule and joule can cancel. So some people might be thinking, well, I'm going to use the unit method, right? And, for 1 kg, the amount of energy I have is 41.8 megajoule. And for 1 meter cube, the amount of energy I have is 34.9 gigajoule. Skip the joule here. The unit for joules is not necessary when representing density. So what do I have left for density? I will have 34.9 times 10 to the power of 9 divided by 41.8 times 10 to the power of 6. On top, there is still 1 kg. Below, there is still 1 meter cube. 9, 8, 6. So I will have 834.9 or 8.35 times 10 to the power 2 kg meter negative 3. Okay. In fact, right, if I have a little bit of chemistry in my brain, I'm thinking to myself, diesel fuel. Diesel fuel is petrol. Petrol less dense than water. What's the density of water? 1000 kg per meter cube. There's only one option that is less dense than water. Everything else is denser than water. So you actually don't need to do any calculation for this one. Unless everything here is like 800 something, 900 something, then like this one, then you will need some calculation. This one can guess the answer. If you know petrol is less dense than diesel, than water, how do I know? I don't know. Too much chemistry in my brain or common knowledge. Oil floats, right? So less dense than water. Petrol is a type of oil. Fuel is a type of oil. All these are oil. Okay, so go practice a bit. You will develop a skill set to be able to do it. But if you die want to calculate, just use the unit to cancel out, okay? And remember to convert the prefix. Don't leave them inside. Okay, next one. We're going to move on to all the pressure measuring stuff. Okay, and as usual, I will do some of the recent questions. You go try the rest on your own, okay? For the pressure measuring equipment, the important thing is to look at the part that is open to atmosphere, because there is this thing called atmospheric pressure. So we know that atmosphere is actually pushing down here, PATM. Okay, and from P is equal to rho Hg. If it's the same material and inside the same planet, same height or same depth will have the same pressure. This is an important concept to remember when you do questions like this. So for example, the pressure here and the pressure here is the same. Let's say this is point A, this is point B. Pressure of A is equal to pressure of B. You have water, but not that concerned. We know the atmospheric pressure, 101 kilopascal. So what is the pressure of the gas from the gas tap? From here, there's obviously gas pushing down. Okay, so you imagine you are standing at A and you look up, what's pressing down on you? The gas flow, because the gas come from the pipe here. So on point A, there's the gas pressure. Move yourself to point B. What's pressing down on point B? Well, there is the atmosphere on top, pushing it down. But also at the same time, there is this length of water, this bit here. So I'm going to represent the length of that amount of water as, I guess I'll just draw an arrow here. P water, H2O. So first step, choose a level. Same height, same pressure. This is the best level to choose. Teacher, why don't you just choose here? If I choose here, I don't know what is this height. I don't know what is this height. I mean, of course, left and right, it will cancel, but it'll be very annoying. Okay, so we choose a point where we're relatively confident we can find all the heights that we need. Okay, so we're looking for the pressure of gas. Atmospheric pressure is 101 kilo. And water pressure is rho Hg. This rho is 1000. Question give one. The H here would be 31.4 minus 10.2. But I have to convert everything into SI. So 0.314 minus 0.102, 9.81. So 101 times 10 to the power of 3 plus. This one is 207. I mean 208 Pascal. So that would mean, if I convert to kilo, this will be 101 times 10 to the power of 3. This is 0.21 or 208 times 10 to the power of 3. Okay. Right, 101 to the power of 3. We don't expect water to have much pressure compared to the atmosphere. Done. Minus 1. Oh, this is 2080. So this is actually 2.1, making this 103 times 10 to the power of 3. Pascal. D. Okay. water pressure is very insignificant compared to our atmospheric pressure, especially when the height is like less than a few meters. So actually our biology is evolved to survive under high pressure. You are designed by God to operate under high pressure. How are you doing? How's life? Okay. So always start the same way, same height, same pressure. Write down the pressure equation. If necessary, use H rho G to convert the pressure as needed and just add them up. All right. So other kind of pressure question could also involve this kind of equation one, where there's a tube like this. But we are still going to do the whole same height, same pressure thing. Okay, so I can't choose this point, although I know Z, because what is going on here? The column doesn't make sense. So the best place to choose is here. Same height, same pressure. Okay, again, I'm going to put AB. You can put whatever initials you want, doesn't matter. Pressure at A is equal to pressure at B. What's pressing down on A? P1. What's pressing down on B? P2 plus this length of liquid, P liquid. So P1 is equal to P2. P liquid is rho Hg. But the H is this one. And I look at all my answers, got Y minus Z or X minus Z. So I guess from here, this H is pretty obvious. It is Y minus Z. So P1 will be equal to P2 plus rho Y minus Z times G. So match the equation. I think the only one that has the option is this one. So P2 brings over and subtract. So you have rho G, bring the constant forward. Z. This one is easy. I'll give you a challenge one to try. Let me open the question first. But if your eyes are quite sharp and you can identify the strange looking questions, you probably have already done that. So this is one U, but we can also ask a double U tube. W tube. This one is summer 15. It's probably already recorded because it's one of those landmark questions. Question 21. If you're looking at using my handout, that will be page 34. Actually, the era of difficult MCQ was about 2014, 2015. Not sure why. Okay. Sometimes they will give you a question like this, where it's totally like a sentence and a scenario. So no diagram, maybe a bit more uncomfortable. But here it's just saying that a bird is diving to a depth of 1.5 meters below the surface of the lake. So you want to find the pressure of this depth. So there is a lake, there is a bird. This bird is 1.5 meters below. So this distance, this is the water pressure that is on the bird. That 1.5 meter of water plus atmospheric pressure. So the pressure here would be equal to atmosphere plus 1.5 meter of water. The pressure of water. So standard operating procedure, you begin to see a pattern. Density of water is 1000, height of water is 1.5, G is 9.81. Okay, so even if you go diving underwater, I believe the increase in pressure on your body is really not that much. This one is 1.16 or 116 times 10 to the power of 3. You increase maybe about 10%, slightly more than 10%. Only when you go deeper and deeper, then only you will get some form of altitude or pressure sickness. Okay. So for a more challenging version of this question, you could try May, June 14, P13, question 22. This is the Mariana Trench, page 34. And there's a pretty infamous question about the average density of atmosphere. Go do this one too. 50. Page 36. If you wonder why the page number the question number jumped so much, is because 2016 is where the new syllabus begin. But yes, this one is hard. This one needs some thinking. It's one of those questions. This one also needs some thinking. It's one of those questions. Spoiler alert, go do the question first before you watch the recording. Okay, but the rest are fairly okay, doable. All right, finally, we're going to look at upthrust. Okay, so for upthrust, normally they will ask you to think about upthrust as another force. So we have that 4 forces: weight, tension, normal, friction. Upthrust is the 5th, the wingman. Okay, but regardless, here we have an object falling through constant speed. If constant speed, this is also a signal that this thing is in equilibrium. Net force is 0. Okay, which diagram shows these 3 forces to scale? Well, I don't know what object this is, but I do know if it's equilibrium, the sum of the forces have to be 0. Okay, meaning to say, I can always do this where I draw on I don't even need to know what forces this are, because just by looking at D, I know this thing can't be in equilibrium. Let me drag the arrow down. So this is length of the first arrow. This is length of the second arrow. Confirm not enough, not in equilibrium. I can also say the same thing for C, right? So in the exam, whenever you see a vector diagram, especially for your objective, understand that they will draw them to scale. So you can always just use your ruler to transfer the line. So you can see this upward force is maybe here, and the other one, would be here. Also not long enough. So this is also out. I think you can tell this one is already long enough to balance the other one. See? So this is also out. So you look at this one. But if I'm going to label the forces, this will be weight. So this spherical object has weight. And then one of it is upthrust. I don't know which one is upthrust, but one of it is upthrust. One of it is drag. Okay. The only caveat here I want to point out, not sure if we've done this question already, but the weight of air bubbles is small. Okay, and this one is falling through water. So falling through water means the direction of V is here. You're falling down now. So the direction of drag or water resistance should be upwards, opposed motion. Okay, but if let's say you talk about air bubble will rise because air is less dense than water. If bubble rises, so this is my air bubble. This one here, my bubble. Air bubble rises through a liquid or oil or whatever. The weight is going to be tiny, right? And because it's going up, the drag force will be quite significant. Okay, why is drag force down? Because the velocity is upward. Okay, and because this thing is very light, so it probably has a significant upthrust also. Upthrust. Okay, So the diagram will look something like this. Don't memorize, be able to identify the forces and their relative magnitudes. Okay. Right. So that's one. Here's another one where you have a metal cylinder immersed in water, hung from a Newton meter. And we are going to raise the metal cylinder slowly by lifting the Newton meter. So we're going to ask to find the variation of R with distance D of the base of the cylinder from X. Base of the cylinder from X. So when the cylinder goes up, let's say when the cylinder reaches here, not drawn to scale, but hang on, let me draw it so that the size is more equal. The base is here, this one is here. Here to here is D. So we start here, D equal to 0. Cylinder is at X. Okay, and right now I realize that most of the graph, the pattern or the shape look the same. The only question I'm going to start with maybe is the first section. Do you think the weight will increase? This R here is the reading on the Newton meter. Or do you think that the reading will stay the same at the first section? So at this section, right, the cylinder is still slowly being pulled up. It hasn't left the water surface yet. From here to here to here. If you think that the upthrust has changed, then the answer is no. Okay, because what affects the Newton meter reading? Okay, I'm gonna just draw the tension here. There's a spring here, and this spring will be able to be stretched based on the tension here. Pull ma. But the equal magnitude, opposite direction, reaction force, will also pull the cylinder upwards. Let me change this to green. So it's going to pull the cylinder upwards here with the same value of T. That's how you can read the reading on the Newton meter. And then there is obviously the weight of the cylinder, W, which is constant. And then there is upthrust. We're going to draw upthrust here. So based on the equation of the forces acting on the cylinder, I'll say that the tension, upward force, is equal to the, what else is upwards? Upthrust is equal to W. Sum of the forces upwards is equal to sum of the forces downwards. Okay, so you can call this upthrust. If it's confusing, because we use the sum of the upwards forces, then you can use FB. B is for buoyant force. Not magnetic force, buoyant force. So you can see that your reading, this is R, the tension in the string. Okay, the reading T or R is equal to the weight minus the force. But what is the buoyant force? Buoyant force can be calculated using rho Vg. This V is the water or the liquid displaced. As long as it is entirely underwater, the liquid displaced is the same. So number one, when fully submerged, FB is constant. So this water displaced is also a fancy way to say the volume of the object submerged in water. So meaning from here to here to here, the value of T is constant. Because I didn't change the upthrust now. So T is the same. So this T should be constant. This is out. This is out. This one is okay. This one is okay. So here is also okay. Here is also okay. Because this point onwards, the cylinder no longer touches water. Here also, okay, no longer touches water from this point onwards. So the question remains would be, should the middle section as it slowly leaves the water be constant or a curve? Okay, so when you think about this middle section, right, this one is, let me continue the water surface first. So now your cylinder is going to slowly, step by step, leave the water surface. I apologize if their sizes don't look the same. Okay, let me draw them a bit different. Okay, so it slowly leaves the water surface. And in this section, you can see that the volume of the water displaced is less and less until 0. So the only question is, do you think it's a straight line or do you think it's a curve? So number one, the velocity of the cylinder is constant. Okay, so let's say I want to think about the volume. Volume of the cylinder inside the water will be equal to the cross-sectional area, which is constant, multiplied by whatever length this is, which is L. But velocity is distance over time. The distance traveled by the cylinder has something to do with the length. So if this one is constant, then in every second, the change in L is constant. If the change in L is constant, what can you say about the change in volume? AL, constant. So if the change in volume is constant, the graph, because, the buoyant force is V rho G, the change in V is constant, the change in buoyant force is also constant. So the change in buoyant force, constant. Hence, if the change in buoyant force constant, look at the buoyant force here, then the change in tension or the change in R also constant. So the answer is C. So here to here constant because fully submerged. Your reading, which is tension, will be equal to the weight of the object minus the buoyant force. This section here, no longer inside water, the reading is equal to W. In the middle here, leaving the water, so the reading is equal to W minus buoyant force is rho Vg. But V decreases uniformly. How do I know? Because velocity is constant and this whole thing here, this one. That's why you get this section here. So as this one gets smaller and smaller, the value of R become bigger and bigger. If you want to get this kind of graph, right, then your shape have to look like this, like some Christmas tree shape. Then this one is possible for this one. Some Christmas tree shape. Can. Okay. So remember, when it's fully submerged, I don't care where the thing is, the upthrust is the same. FB constant. Okay, so the remaining ones are the ones that is pivoting on derivation, I guess. So for example, for this one, you have two blocks, X and Y. You are given the dimensions of all the blocks. And block X is placed in a liquid of density rho with shaded face level with the liquid surface, it experiences upthrust. Okay, I write equation. For block X, the upthrust is equal to U. Sure. So U will be equal to rho Vg. The density is rho. The volume looks like A cubed. Throw inside first law, don't know what to do, just write only. This is U. Okay, part one side. Do a second one. This one has a slightly different shape, but block Y is placed on a liquid of density 2 rho. Interesting. So I repeat again. This U, let's say this is Uy. Don't know what Uy is, but I'm looking for it. The density, the volume, gravitational acceleration. But this density is 2 times. Okay. And to find the volume, it will be 2a multiplied by a multiplied by half a. And then in the back is still g. This is 2 rho. 2 times half just goes away. So what is here is a cubed times g. Do we know what is rho a cubed g? Rho a cubed g. So you can see that the new block will have twice the upthrust. Okay, because this thing is the same as this thing. 2u. Okay. So whenever they give you a scenario like this, I don't care whether it's an upthrust question, pressure question, density question, Young modulus question, some other question. If you know the equation, just put it in and trust that you can simplify it later. Okay, they are okay. Which means I'm going to leave this to you. By the way, I feel like this one is a trick question just by reading. For example, it says here that this is a solid block and the upthrust is U. The block is now rotated to a new position so that the face with the smallest area is horizontal. So what they're going to do is they're going to flip this block. Ding. Something like that. Let's not change the dimensions. So the block will look something like this. The smallest area is horizontal. The block remains fully submerged. You know why I know it's a trick question? Because I saw these 3 words. So if it remains fully submerged in the surface of the water, why should I care? The volume, the same. Volume of water displaced is still the same as the volume of the block. So the upthrust is still. Go watch the derivation video where I satisfyingly cancel out the area of the block. That means it does not matter. When you have a larger area, sure, you have more water pressing down on you. So you may think that you have more pressure or more upthrust, but you don't, because you also have a large area to disperse the weight. So it doesn't matter. Okay. Refer to the equation if needed. Refer to the derivation if needed. Okay, here's a slightly different one. This one, you're asked to derive the upthrust acting on the block from the liquid. But in terms of density, but you have density of the block of wood, I think, and the liquid. So liquid is rho L. And the block is rho W. But whenever we look at upthrust, maybe I'll write it in the notes here. Use this equation, right? This density is due to the liquid displaced. So it's density of displaced liquid. The one that you are submerged in, okay? Then this volume is the volume of liquid displaced. My focus is on how much water level rise. I don't care about everything else, because this equation actually has roots in this equation. So if density of fluid is here, density of the fluid is also here. It's the same thing, okay? So if you go back to the question just now, this one, if I want to find the upthrust acting on the block, this upthrust will be equal to density of water, volume of the water displaced, gravity. But the volume of the water displaced, because this is fully submerged, is actually a to the power of 3. So like that. Why did they give you the other things like the density of the, wait, this one is a liquid, not wood, sorry. On the block from the liquid. Why did they give you the rest? To probably confuse people. Okay, so block density is rho W because it's wood, and the liquid density around it is rho liquid. So whenever you think about upthrust, the main character here is the liquid. The liquid that is being displaced, the liquid density that matters. It just so happened that the liquid that is displaced is the same as the volume of the object, as long as the object is fully submerged. And of course, you might be thinking, what happens when the object is not fully submerged? Well, I'm glad you asked. Go do this question. Not fully submerged. Go try May, June 19, P11, question 12. Page 38, if you are using my topicals. Go do lah. Then come back and ask questions. You go try first. Okay, so finally, we'll leave this here to you. I think this is, again, fairly straightforward. They like to ask a lot of, concept questions like this. But they're asking you what change can increase the magnitude of upthrust. I write equation. Upthrust is equal to rho Vg. I don't care about the density of the block. Do I care about density of the block? Held vertically. Density of the block is the same as the density of water. So that means it's just going to float here, no? Okay, sure. Hold the block horizontally, it's not going to change anything. Increase the dimension of y. Make the block longer. I'm assuming if you keep the dimension of y longer, you don't change x, right? So the answer is C. Because volume increase, upthrust would increase. Okay. You could also increase the density of the liquid. Other options include increase density of liquid. All right. I think finally I want to talk about this bear. Because this bear is also partially submerged. I do this one, you go do the other one. Okay. So my friend here is chilling on a ice. Global warming. Although the ice piece looks very uniform, sure. But anyway, the cylindrical block has a cross-sectional area of this much, and it's floating, partially submerged in the sea. Partially submerged, right, means that, although it's not drawn, a little bit of ice underneath the water surface. Okay, a little bit, not sure how much. Okay. So we have the density of the seawater, and you have a polar bear standing on the ice. I'm wondering if the ice itself has weight, but never mind. The block of ice sinks a vertical distance of d. So this sinks when the polar bear steps onto the block. So meaning, right, before the polar bear, it already sink a bit. Now you put the polar bear on top, it sinks some more. Okay, before the polar bear, the ice is already partially submerged. After the polar bear, it sinks further. But I want to find what's the further distance d. Okay, so maybe this was the initial one. Okay, this is the initial part where it's already sinking. And then now, because of the polar bear, sink some. Okay. So I can say that the change, triangle for change, the change in weight of the iceberg polar bear causes the change in upthrust. And this change in weight is due to this polar bear, 400 times G. He steps on the ice sink a bit to displace more water so that he can float. Okay, what is the upthrust? Rho of water, volume of water displaced, G. But the one that has changed is not the density of the water, but the volume. Because the bear sinks some more, so the water level rise some more. Okay. Regardless, I can cancel the G. Okay, bye-bye. So on one side, I'll have 400. On the other side, the density of seawater is 1020. And the change in volume will be the cross-sectional area multiplied by this sink a further distance d. Okay. So 400 is equal to 1020. Cross-sectional area is 12 meters. Already SI, no need to convert D. So you can find how much the ice sink. Okay, so this one will be 0.0327 meter. I guess if we convert to cm, 3.27 cm. Okay, not too much. Also, you can sort of use logic lah. This one is 32 cm, which is like entire length of your long ruler you used to draw graph. So it's like a bit sketch. This is totally out. Normally, when we give you a real life scenario, it has to be a number that is logical. It cannot be some random number that is that you cannot, think about what is going on. 3 meters sinking. I'm not sure how the polar bear managed to climb up 3 meters. How to step up a 3-meter tall ice. Even stepping up a 32 cm height, it's about this height. Quite tall. Okay. So your answer should be logical. If it's not, probably there's a conversion error. So upthrust questions are doable. This is generally the easy section of the syllabus. So in the meantime, I have selected some that you can try. The interesting one that I want to point out here is number 1. This one that combines upthrust and tension in the spring. So we'll try this one. Okay, I know there is some elastic potential energy. We can talk about that later. And also this one, you know how just now the graph we draw, the speed is constant. So you move the cylinder up at constant speed. This one, it no look very constant to me. So go try lah. Okay, so go try the 2 questions, or basically finish out what is left behind. And I think just to give you a sneak peek about work energy power that we will go in depth next time I see you. When it comes to work energy power, as you study, right, the derivation for this is important, because what is force at the end of the day? Force causes work done. 1, 2, 3. Force causes pressure, force causes acceleration, force causes rotation. I think I'll just write down here. Number 4, we need to look at work done. In other words, when there's acceleration, force causes a change in energy. By the way, for example, if you change motion, your KE changes, right? So energy is a nice way to tie a conclusion into mechanics, because we know, or we've been doing some questions and they ask you to find kinetic energy lah, they ask you to find GPE lah. Now we tie everything together. So force causes a change in energy, right? Then I didn't really sort the paper 1 question because I think Cambridge does it very well. They already sort such that every variant among the, so let's say you look at P11, 1, 2, 3, 4. If you look at these 4 questions, normally there will be 1 that is a statement, and then there will be 2 that is calculation, or 3 that is calculation, and then 1 of it is a graph. So oftentimes when it comes to energy, there is a significant combo. So if you look at the questions I've selected, it starts from the derivation of energy. And then we can start easy by converting between kinetic and GPE. This one is what you are very familiar with. Then the block swing up, lose KE, gain GPE, swing down, lose GPE, gain KE. Okay, so I think that one is okay, not a problem. In fact, this one looks a bit like a combination of moment of forces and energy. Go try the question. Like for example, when the child jump up, go down, conservation of energy. Okay, but or when a car travel up from A to B, let's say he slows down, then it will be KE convert to GPE. So the main outcome that you want for yourself is you are able to actually visualize the energy conversion. If not, we can practice, and we will be practicing some next round. Okay. And then, of course, plot twist, they can combine KE, GP, and elastic PE, because why not? Right? For example, I can compress a toy car, and then I store some elastic potential energy in the car go wee, loop the loop. So as the car travels, it has KE converted from elastic potential energy. That KE will convert to GPE, GPE convert back to KE, slide down. But if there is friction, average resistive forces, there's also some energy loss as heat. Okay, so I have a selection of all of these GPE, KE, elastic PE interaction. This child is sliding down a slide, and then at the end of the slide, in order to break the child will compress a spring. So this is different. GPE to KE to elastic PE. So go visualize the question if you can reach here. If not, focus more on chapter 4. Or I know for a lot of people, trials are coming soon. If you want to, you can study your trials as well. Send questions to the Discord. I will try to find time to answer them. Okay. And then sometimes we will focus a lot on P equal to FV as an equation. So these are normally asked in inclined planes. If you struggle with inclined planes, you see a lot of them in conservation of energy, because it's a perfect setting to show the conversion of GPE and KE. So they will ask a lot of inclined plane questions. All right. So I've selected some of the more important one for different concepts. And then we will start chapter 5 next round, because I think 2 hours of physics is enough for you and for me. Though for me, it's definitely more than 2 hours today. But hey, I'm not learning new stuff. You are. I'm not doing revision. You are. Okay. So we're going to unpack or unlock this level next time. And then we can draw mechanics into close. Okay. So in the meantime, just a reminder, if you look at the Google Drive for your AS, the video notes is already updated to chapter 6 for your studies. And then I understand that some people ask for more chapters. I will do so probably within these few days. Maybe not tomorrow, because tomorrow I have a pretty full day, but I will try to do it maybe Monday or Tuesday next week. Okay, so that you can use it if you want to study. All right. So for your trials, my only comment is topics that you have done, try out the questions as if you are sitting for exams. Let's say, for example, your revision didn't cover certain topics, then it's okay to let them go first. But try to figure out what are the mistakes that you tend to make and what are your weaknesses, whether it's explaining, calculation, or graphing. And then you can also let me know, or be a bit more intentional in choosing those questions, targeting your weakness to solve physics. Because at the end of the day, it's still the same. Can you explain? Can you calculate? Sometimes with some derivation. And can you show that calculation in a graph and vice versa. Okay, as usual, everything you need will be on Discord. Let me know if I can help you throughout the week. In the meantime, take care. Good night. Stay safe. Thank you.